Good day, everyone. Our lesson for today is all about conditional and biconditional statement. The objective for this lesson is you will be able to write conditional and biconditional statement in if then and if and only if form. Label parts of a conditional and biconditional statement, construct truth tables, and value the nature and importance of mathematics as language and symbol. So, what is conditional? Conditional, the statement if P, then Q, denoted by P implies Q. Read as P implies Q is called an amplification of conditional statement. P is called the hypothesis and Q is called the conclusion. The truth value of a conditional statement can either be true or false. In order to show that a conditional is true, just show that every time the hypothesis is true, the conclusion is also true. Also, if both the premises and conclusion are false, the conditional statement is false. True, rather. To show that the conditional is false, you just need to show that every time the hypothesis is true, the conclusion is true. If you can find just one single example such that the hypothesis is true but the conclusion is false, then the conditional is false. So for the conditional, the P statement is the hypothesis and the Q statement will be the conclusion. So we have here the truth table of F then. So we have here two statement. We'll let that one as P and Q. Then our compound statement in if then connectives. So we have here our first simple statement is true. Then the second simple statement is true. Our truth value of truth value of the compound statement and if then statement is true. So for the second one, if the hypothesis is true, our conclusion is false, then our conditional statement is false. For the third one, if our hypothesis is false and our conclusion is true, our conditional statement is true. For the last one, if the hypothesis is false, then our conclusion is false. Our condition, conditional statement is false. So what have you observed with this table? So the conditional or if then is if both hypothesis and conclusion is false, the conditional statement will be true. And also, if both of the hypothesis and conclusion is true, our conditional statement will be true. So if the hypothesis is true, then the conclusion is false. So our conditional statement will be false. All right. So we will based on the conclusion. No? If our conclusion is false statement, therefore our conditional statement will be false. So we also have here if the hypothesis is false, then our conclusion is true. Therefore, our conditional statement will be true. Again, it will also depend on the conclusion. No? So since our conclusion here is true, therefore our conditional statement will be true. Okay, so it will apply on this. It will apply on the if there is a difference truth value of hypothesis and conclusion. No, so if both false and both true, therefore our conditional statement will be true. No, so that's the conditional. So say for example, we have here will let P John eat fries and let Q Maria drink soda. Construct the following conditional proposition. So we have here our first symbolic form. We have here P implies Q. Since it is amplification, so we'll start with the word F followed by then. So since our P here, we let the P as John eat fries. Therefore, if John eat fries, then we proceed that then the word then next is Q. So our Q here is Maria drink soda. Therefore, our statement will be that if John eat fries, then Maria drinks soda. For the second symbolic form, we have here Q implies P. So again, let's start with the word F, followed by then. So we let Q as Maria drinks soda. Therefore, if Maria drinks soda, then John eat fries. For the third one, we have here, we start again with the F, followed by then. So we let P as John ate fries since it is a negation of P or not P. Therefore, our statement will be if John does not eat fries, then we let Q as Maria drink soda. So we have here then Maria drinks soda. For the symbolic form of not P implies Q, the statement will be if John does not eat fries, then Maria drinks soda. Alright, so we have here another example. So let P, one half is an integer. So we let Q as a square, R circle. So we will determine the truth value of P implies Q. So for P, the statement of P is one half is an integer. This is a false statement. So we let Q as a square, R circle. So this is also a false statement. So if we have a compound statement using the amplification connective, so we have here if one half is an integer, then square are circles. So what I said earlier that the conditional, if both of the hypothesis and conclusion is false, therefore our conditional statement will be true. That is why this compound statement is true. Alright? So that is the conditional. So we also have here the variance of conditional statement. Given conditional, if P then Q. So we have here P implies Q. For the converse, we have here if Q then P. So we have here the symbolic form Q implies P. For the inverse, we have here, if not P, then not Q. So the symbolic form will be not P implies not Q. For the contrapositive, if not Q, then not P. The symbolic form will be not Q implies not P. So let's have here the example. Consider again the conditional. If it is raining, then there are clouds in the sky. So this is a form of conditional. So RP here is if it is raining, then RQ here is then there are clouds in the sky. So it seems reasonable to assume that this is true because we cannot say that when it is raining, then there are clouds in the sky, no? So for the converse, we have here the converse would be if there are clouds in the sky, then it is raining. This is also not always true. No, we cannot always say that if there are clouds in the sky, then it is raining, no? So for the inverse, we have here if it is not raining, then there are not clouds in the sky. Likewise, this is not always true. We cannot say that if it is not raining, then there are not clouds in the sky. No? So, for the contrapositive, we have here, if there are not clouds in the sky, then it is not raining. So, this statement is true and is equivalent to original conditional. Alright, so we have here the truth table of conditional, contrapositive, converse, and inverse. So we have here two statements. We have here the P and Q. P is the hypothesis, Q is the conclusion. So we have here true, true, false, false, true, false, true, false. So first is we get the negation of P. So the negation of P, we have here since it is true, so the negation will be false. Then a statement is true, the hypothesis is true, therefore our negation is false. Then we have here also that false statement. So the negation of P is true, then the statement is false, the negation is true. We also have here the negation of Q. So we have here True, so the negation is false. False, then the negation is true. True, then the negation is false. False, then the negation is true. So first, we get the truth value of conditional. So we have here P implies Q. So P implies Q, true implies true, so that is true. True, true statement implies false, so that is false. Like I said earlier, that if there is a difference between the hypothesis and conclusions truth value, you will only look for the truth value of the conclusion, then you can conclude that the conditional statement will be uh false, no? If the conclusion is false, no? So since we have here true implies false, that is, so the conditional statement will be false. So we have also here, we also have here false implies true. So true statement, so the conditional statement will be true. So we also have here false implies false. So since it's the same, okay, same, they are the same truth value. Therefore, our conditional statement will be true. No. So for the inverse, we have here not Q implies not B. So we have here not P. Not P implies not Q. So we have here false, so that is true. False true, so that is true. No. Okay. True, we have here true conclusion. So we also next is true false. So our conditional statement will be false, no? Then true, that is true. For the converse, we have here Q implies P. So Q implies P. So we have here true, so that is true. False true, so our conclusion is true, so that is true. True false, our conclusions will is false, so that is false. Then false, so that is false, no? So the converse will be true, no? So this is now the truth value of our converse. So for the contrapositive, so we have here not Q implies not P. So we have here not Q implies not P. So RQ or not P is false, then not Q rather is false, and not P conclusion is false. So we have here false, so that is true. Then true false, so that is false. False true, so that is true. True, so that is false. Alright, so that's our truth value of conditional, inverse, converse, and contrapositive. So we have here, notice that the column of truth value under conditional P implies Q and its contrapositive are the same. When this is the case, we can say that the statements are logically equivalent. In general, two statements are logically equivalent when they have the same truth table. Similarly, the converse P implies Q and the inverse um, P implies Q have the same truth table. Hence, the two are logical equivalent. So, a conditional statement and its contrapositive are logically equivalent. The converse and its an inverse of the conditional statement are logically equivalent. So, the conditional and contrapositive is logically equivalent. So we have here, our conditional is, the truth value of our conditional is true, false, true. And also, for the contrapositive, we have here true, false, true. Therefore, conditional and contrapositive is equivalently, logically equivalent. No? We have here logically equivalent. So, same goes with inverse and converse. The truth value is true, false, true. For the converse, we have here true, false, true. Since they have the same truth value, therefore, they are logically equivalent. Alright? So, we're done with conditional, let's proceed to biconditional. So, what is the biconditional? The connective P, if, and only if Q is called biconditional and written as this one, P, if, and only if Q, is the conjunction of P implies Q and its converse, Q implies P. That is, P, if, and only if Q is logically equivalent to P implies Q and Q implies P. The truth table of P, if, and only if follows. So we have here two statement. We have P and Q. Then the truth value of P is true, true, false, false, and the truth tables of Q is true, false, true, false. So P implies Q. We have here true, false, true, true, and Q implies P is true, true, false, true. So first we get the unconnective for these two conditional. Right? So we have here P implies Q and Q implies P. Since we already have the truth value of P implies Q and Q implies P, then we get the unconnective for this, no? So for the unconnective, again, like I said, that the unconnective is in favor of false statement. Once one of the simple statement is false, automatically our and connective will be false, no? So we have here true, true, that is true. So false, true, that is false, since we have here false statement. So true, false, we also have here false statement, so that is false. So we have here two true, so that is true. The condition for biconditional is you can determine the value of biconditional by getting the truth tables of P implies Q and Q implies P. The P implies Q and Q implies P is logically connected with P, F, and only if Q. So since the truth table rather, of P implies Q and Q implies P is true, false, false, true, therefore our P, if, and only if Q is true, false, false, true. So that is how we get the truth table of biconditional. Alright, so note this that biconditional P, if, and only if Q is true when P and Q have the same truth value and false otherwise. Often, in mathematics, the word necessary and sufficient are used to describe conditional and biconditional. For example, the statement, water is necessary for formation of ice, means if there is ice, then there is water. Similarly, the statement, a rectangle with two adjacent sides, the same length, is a sufficient condition to determine a square. Means if a rectangular has two adjacent sides, the same length, then it is a square. Symbolically, we have the following. P implies Q means Q is necessary for P. P implies Q means P is sufficient for Q. So, P if and only if Q means P is necessary and sufficient for Q. So, we have here example for biconditional. So, will it be as John eat fries, then Q Maria drink soda? Construct the following biconditional proposition. So, we have here P if and only if Q. So, RP here is John eat fries. So, that is John eat fries. Our connective is if and only if. So, that is if and only if. Our Q here is Maria drink soda. So, the symbolic form of P if and only if Q will be John eat fries if and only if Maria drink soda. For the third symbolic form, we have here Q if and only if P. So the statement will be Maria drinks soda. Since we let Q as Maria drinks soda, then our connective will be if and only if. And P is John ate fries. So the statement for the symbolic form, Q if and only if P, will be Maria drinks soda if and only if John ate fries. So for the last one, we have here not P if and only if Q. So will that be as John ate fries? So therefore, John ate fries. Since it is negation of P, therefore, the statement will be John does not eat fries. Then our connective will be if and only if, and we let Q as Maria drink soda. So we have here Maria drink soda. The statement for this symbolic form, not P if and only if Q, will be John does not eat fries if and only if Maria drink soda. We also have here another example. We let P, 1/2 is an integer. We let Q as square R circle. So determine the truth value of P if and only if Q. So we let P as 1/2 is a integer. So that is a false statement. And we let Q as square R circle. So this is a false statement. So the compound statement using if and only if uh, connective. So that is 1/2 is an integer if and only if a square or circle. So this is true. Why is this why it is true? So if we look to the tabular, no? So our hypothesis and conclusion is false and false. So if we have here false and false. Our P implies Q and Q implies P is false. Therefore, our biconditional or P if and only if Q is true. So that is our statement here is true, no? So that is how we get the truth value of biconditional. So we're done with conditional. Okay, so we have here check your progress. Write the following in symbolic form using P, Q, and R for statement and the symbolic. We have here not, or, and, if then, and if and only if. So we have here. Alright, you answered that one. Okay, check how you progress. Okay, thank you everyone.